Alright, we're in the fourth video in chapter 13, and we just looked at heat and a lot of heat problems. Keep practicing those. We're going to talk about intermolecular forces now, because we mentioned this at the beginning of the chapter, that liquids have intermolecular forces of attraction that are relatively strong, holding them together, versus gases, which is why they remain in close contact with one another. Not as strong as solids, though, which is why they still move around versus remaining rigid in shape. So they're mobile and they can flow. So we know that liquids have intermolecular forces of attraction holding them together. And we mentioned earlier that different liquids have different inherent intermolecular forces. Why is that? If you compare the intermolecular forces of attraction of water with methane, with carbon disulfide, with ethanol, with diethyl ether, with acetone, all of these different substances, we notice that the intermolecular forces of attraction are different because these are different molecules that have different bonds making them up. And it turns out that they have different types of intermolecular forces depending on the types of bonding in the molecule. So we're actually going to talk about three different types of IMFs, or intermolecular forces. The first type is something called dipole-dipole attractions. These are intermolecular forces that are found in covalent molecules. Remember, covalent means molecules that share electrons. So covalent molecules exist between nonmetals bonding with nonmetals. And in these molecules, due to atoms having different electronegativities, there's polarity differences in the compounds. Remember what differences in electronegativity are. If you have a periodic table, I'm just going to draw one quick. Remember, the most electronegative atom is fluorine, right, found right over here. The noble gases don't form bonds, so they cannot have different electronegativities because it's a bonding unequal pull of electrons in a chemical bond. But fluorine's the most electronegative, and all of the other atoms are less electronegative than fluorine. And the general trend is as you go up a column or across a period, a group or a period, you become more electronegative. So fluorine's the most. So in bonds of nonmetals bonding to nonmetals where there's differences in electronegativity, you build up a dipole. An example of this would be like a molecule of, let's say, acetone. Or actually, let's look at formaldehyde because it's really easy. Alright, formaldehyde here has two different types of bonds. It's got a carbon-hydrogen bond. And remember we said that carbon and hydrogen have about the same electronegativity. Hydrogen's one of those weird ones on the periodic table that's found in different places. So this is a nonpolar bond, which means there's no difference in the charge on hydrogen versus carbon because there's equal pull of the electrons in that bond. The second type of bond we have here, there we go, is a carbon-oxygen bond. And I totally shouldn't have done that. Okay, a carbon-oxygen bond. Oxygen on the periodic table, so we've got carbon, nitrogen, oxygen, fluorine, right? So this is if you look at this part of the periodic table, these atoms are all in the same period. And carbon is to the left, oxygen is to the right. We know that oxygen is more electronegative than carbon. Because of that, this is a polar bond. Remember we showed polarities, these dipole moments, and it means that carbon has a partial positive charge, and oxygen, being more electronegative, has a slight partial negative charge. So there's partial charges in this compound. Because there's different charges, remember, opposite charges interact with one another. So if I have a second molecule of formaldehyde, for instance, in my compound, once again, I know that the carbon's partially positive, the oxygen's partially negative. What's going to be attracted here? Well, we know by Coulombic laws that opposite charges attract one another. So the carbon here, which is partial positive, is attracted to another molecule's partial negative charge. So they're attracted here by opposite charges. This is an intermolecular force of attraction. It occurs intermolecular are the forces of attraction between two different molecules of the substance. So this intermolecular force which exists is a coulombic force, the positive and negative charges attracting one another. This is a dipole-dipole intermolecular force of attraction. Oppositely polarized portions of the molecule interacting with one another. The interactions between dipoles in different molecules are called the dipole-dipole forces. There's a second type of intermolecular force that exists. The second type is an intermolecular force that's stronger than dipole-dipole called hydrogen bonding. Hydrogen bonding. What hydrogen bonding is, it's a very strong intermolecular force of attraction that occurs between molecules. Which molecules does it occur between? Well, notice the word hydrogen there. Whenever a hydrogen is directly bonded to either a nitrogen, oxygen, or a fluorine atom, that hydrogen-nitrogen bond, hydrogen-oxygen bond, or hydrogen-fluorine bond is a very, very, very polar bond. The differences in electronegativities is very great. Because of it being so high in polarity differences, there's a strong partial charges present in these molecules. So for example, if a molecule has a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen, or the hydrogen bonded to the fluorine, anywhere in that molecule, if you see that, these are very, very, very polar bonds. Oxygen is more electronegative than hydrogen. Nitrogen is more electronegative than hydrogen. And fluorine is more electronegative than hydrogen. The hydrogen will have a very positive partial positive charge. And the other atom, I'm going to call this HX, okay, in polarity here. The hydrogen bonded to nitrogen, oxygen, or fluorine be very positive. The other atom will be very negative, okay? So if there's more than one molecule present, like you have another molecule with HX bond being oxygen, nitrogen, or fluorine, once again, partial positive, partial negative. Opposites will attract. The very, very negative charge of the nitrogen, oxygen, or fluorine will be very attracted to the hydrogen, which is positively charged, and you'll get a very strong, very, very, very strong intermolecular force of attraction. Notice, this is not a real bond. Hydrogen bonding is not a real bond. It's an intermolecular force between two separate molecules due to polarity differences. Hydrogen bonds are much weaker than full ionic bonds, so full charges. But they're very strong intermolecular, the strongest intermolecular forces that exist. Here's some examples of compounds that can hydrogen bond. So if something can hydrogen bond, by the way, it has very, very high boiling points compared to other compounds that cannot hydrogen bond. Let's look at an example here between water and methane. Methane, we said, was a gas at room temperature, and water is a liquid at room temperature. However, they both have the same molecular weights, so their masses are the same. You would expect the kinetic energies to be the same, and you might expect, if you didn't know about intermolecular forces, that the particles would be in the same physical state at the same temperature. Water, though, the structure of water, it's bent overall. We draw the Lewis structure here. This is the structure of water, and here is the structure of methane. I'm going to draw it three-dimensionally for you. You can go back and study chapters 10 and 11 if you want to know how to draw the Lewis structures, convert those to the three-dimensional structures. All right. Now notice in water, there's an oxygen-hydrogen bond. This is an example when hydrogen is bonded to either oxygen, nitrogen, or fluorine. that molecule is hydrogen bonding. Hydrogen bonding is a very high intermolecular force of attraction. If your intermolecular forces of attraction are high, it takes more energy to break those intermolecular forces, so you typically have higher boiling points and higher melting points. Water has a very high boiling point for its low molecular weight. It's 100 degrees Celsius. So that's why this compound is a liquid at room temperature. If we compare this to a compound like methane, which has no polar bonds, methane only has carbon-hydrogen bonds. All four of them are carbon-hydrogen bonds. We said earlier that carbon-hydrogen bonds have no differences in electronegativity. Because they have equal electronegativity values, this is a non-polar molecule, which means it's no charge whatsoever. Because it doesn't have any charge, this one has strong charges, positive, partial negative, negative, partial positive. Because this has charges and the one on the right, methane, does not, the intermolecular forces of attraction are very low. If you have low intermolecular forces of attraction, you typically have lower boiling points for your molecules. So water is a liquid because it boils at such a high temperature to become gas because of the intermolecular forces of hydrogen bonding. The strongest intermolecular forces that we know exist occur in this compound. Methane does not have any. There's plenty of examples of this. Water is not the only compound that hydrogen bonds. Ethanol, CH3, CH2OH. Ethanol, a substance you probably have heard of in most alcohols, has an oxygen-hydrogen bond as well. That is a polar bond. The oxygen's negative, the hydrogen's positive. There's intermolecular forces. If I have another ethanol molecule here, OH. Once again, another polar bond exists here. Partial negative, partial positive. The positive charge of one molecule will attract the negative charge of another. That force of attraction, the higher the charge differences, the higher the force of attraction between those atoms, the stronger the intermolecular forces, and then the higher the boiling point. So hydrogen bonding really increases the boiling point of substances. Substances with hydrogen bonding will boil at higher temperatures than those substances of equal molecular weight without hydrogen bonding. Now there's a third type of intermolecular force that we want to know. So the first was dipole-dipole. These are molecules that have polar bonds, okay? And then we said that hydrogen bonding was a special case where the intermolecular forces were very strong because the bonds are so polar. It's when hydrogen's bonded to nitrogen, oxygen, or fluorine. And now we're going to look at the third. And the third type of intermolecular force is called London dispersion forces. London dispersion forces. London dispersion forces are intermolecular forces that occur in molecules without dipoles. They intermolecular forces of attraction that occur in molecules that do not have dipoles. So what's happening here? Well, if a molecule doesn't have a dipole, then it has no charges. Overall, we'd say those molecules were nonpolar. Oops. Thinking faster than I'm writing. So these are nonpolar molecules. What happens is, even nonpolar molecules have charges inside of them. Because what we learned early on was that inside of every atom, there's a positively charged nucleus with electrons, or protons and neutrons inside the nucleus. And outside of the nucleus are electrons involved in bonding. So if I have nuclei here that are bonding together, the electrons are overlapping, we get a pair of electrons. That's where a chemical bond is. But we know, according to the wave mechanical equation, that you form molecular orbitals, and those molecular orbitals, the electrons can be found in different places. So when I go and I take when I take two atoms and bond them together, the nuclei of those atoms are positive, and we form a molecular orbital in which electrons can be found. And usually if it's a bond, there's at least two electrons there. But those electrons move around the nuclei, and they can be found in the region of space called the molecular orbital. Those electrons are not stagnant, they move around. So there's a point in instantaneous space where those electrons can be far apart, or those electrons can be close together. Those electrons can be inside, in between the two nuclei. They can pretty much be anywhere. So instantaneously, let's say I have two molecules that come side by side. And let's just say I'm showing the bond here. So we have my two molecular orbitals. There's electrons in both of these orbitals. Okay? The electrons, we know, as the molecules start stacking, the electrons actually repel one another because they have similar charges. So what ends up happening is, if the electrons are lined up right here, or on this side, the electrons in the other molecule might instantaneously flee from that negative charge, repel, and we end up creating kind of a positive-negative center on our atoms. I'm going to erase this so I can make this better. In our molecule, we've got the positive charges here. The molecules, nuclei don't move, but the electrons can. So what can happen is, if the electrons move down a little bit instantaneously in one molecule as they're moving around, if the negative charge migrated toward the bottom of that molecule, toward the next one, the electrons here would repel and they would move down as well. Well, if there was another molecule here, protons inside the nucleus, electrons outside, when those electrons move down, the electrons inside this molecule would also flee as well. And instantaneously in space, because we know the electrons keep moving, what would happen is the electrons would disperse, right? And they would repel one another, and we'd end up creating charge across the molecule. If the electrons move down here, we would say that this part of the molecule would be partially positive charged. If the electrons were here, okay, then we'd say the negative charge was down there. That would leave the protons on the top side of the molecule exposed, and we'd have our positive charges here. So overall, I'm just going to get rid of the inside of this. If you have a molecule, it has a positive and negative charge in instantaneously. Like I said, if there are other particles around, the electrons would flee or repel, and you would end up creating a temporary dipole in your molecule. This is a temporary dipole. Partial negative on one side of the molecule, partial positive on the other. So these temporary dipoles that are created end up creating small attractive forces between the small charge differential where the electrons move and expose the nuclei, to where you would get the London dispersion forces of attraction. These small instantaneous temporary dipoles developed. Now what happens then if these electrons here, that was just an instantaneous time and space, decide to move back up and over? Well, once the electrons move back up, they're no longer here. They might move back up here. These electrons then would not be repelled by them anymore, the ones below here, and they could move instantaneously in space again. So we see that these dipoles aren't concrete. They're temporary dipoles. Wherever the electrons are, the clouds move in such a way to create the temporary dipole, and it changes and changes and changes. So what the London dispersion forces really are, let's read the definition again, is they're molecules that don't have dipoles overall, because there's no differences in electronegativities between the atoms, but they can interact with one another and have intermolecular forces of attraction, even though they're nonpolar, because of the uneven instantaneous charge distributions that occur due to electron movement in nonpolar molecules. So these are temporary dipoles. And I'm going to put that they're very weak too. So what kind of compounds have temporary or weak dipoles? Compounds that are nonpolar. We said there are two classes of nonpolar compounds, all the way back in probably chapter 10, I want to say. We said the first class are compounds where you have atoms bonded to one another, the same atom. An example of this might be oxygen, molecular oxygen bonded to itself. When you have the same two atoms bonded to each other, chlorine, Cl2, so we've got O2, Cl2, there's no difference in electronegativity of the atoms, so there's no change in dipole. So they're nonpolar compounds. So they will only have London's dispersion forces. The second time we said you could have a nonpolar compound is anytime you have carbon bonded to hydrogen, like in hydrocarbon compounds. Carbon and hydrogen are nonpolar overall. They have the same polarity or electronegativities. So overall, these hydrocarbons, remember that's what we called them, are nonpolar. Now, remember that London dispersions are very weak forces. So hydrocarbons in general, like methane, ch4 we mentioned earlier, have very weak intermolecular forces of attraction. We said if you have low intermolecular forces of attraction, you typically have very low boiling points. Because the particles aren't held tightly together in the solid or liquid phase, they easily break apart from one another at low temperatures. Okay. Now, I did expand upon the intermolecular forces section from your notes a little bit because I didn't want to just gloss over the intermolecular forces. So everything I covered here is actually in the notes outline that I provided, but I wanted to expand on it because I wanted to not only talk about hydrogen bonding, like in water, which is why water has a really high melting point and boiling point. It's got really high intermolecular forces. But I wanted to talk about why other compounds have lower boiling points. The London dispersion forces, the dipole-dipole interactions, which are strong but not the strongest. So hopefully now you've got a really comprehensive view of the intermolecular forces. We're going to move on to talking about hydrates now. And hydrates are compounds that have water in the crystalline lattice trapped in there. So let's get our notes back out for that. And we'll be looking at the hydrates in the next video and wrapping up the chapter.